welcome back. Our video series on laboratory safety continues with a look at something that affects every aspect of our lives, even in the lab: energy. Today we will look at energy calculations in the lab. That's where we evaluate the potential energy release in a system. This is a critical step to take before you start your project. First, let's start at the end. What happens if you don't calculate the potential energy release in a system? Well, the consequences could potentially affect your safety. Think equipment failure, loss of primary containment, laboratory damage, and the possibility of injury to you and your coworkers.
To start, let's work through an example problem to show how to evaluate the energy hazards for a laboratory process. But keep in mind, this is not an exhaustive look at energy calculations. We will show you just a few of the common techniques used in assessing energy hazards. If you have questions, be sure to follow up with your supervisor. Later, we will list some additional resources you can use to evaluate the energy release of your own experimental work. Here we go. In our example, let's look at a catalyst project to examine the selective oxidation of orthoxylene to phthalic anhydride. By using the enthalpies of formation for the reactants and products found in thermochemical tables, we can calculate an overall enthalpy of reaction. And remember to consider other potential side reactions. Those are equally important as you assess the hazards of this process. These can include the oxidation of the phthalic anhydride product or the complete combustion of xylene. After doing all the calculations of the enthalpies of these reactions, we see that the complete combustion of xylene has the largest potential energy release. And we have identified the worst-case scenario for this particular system with regard to its energy release, the complete combustion of the feed material. But hold on! It's important to remember, just because you evaluated the worst-case scenario doesn't necessarily mean it will happen. We could take certain steps to mitigate the hazards, such as operating under oxygen-poor conditions or at small scale. However, it's smart chemistry to base evaluations of energy release on the worst-case scenarios. Even if they never happen, we have a reasonable margin of safety for the project. Imagine you are working with this scenario. The oxidation of orthoxylene is to be studied in a continuous stirred tank reactor, or CSTR, at 340 degrees Celsius and 285 pounds per square inch gauge, or PSIG. The reactor vessel has a pressure rating of 2,950 PSIG and a rupture disk that is designed to burst at 2,000 PSIG. Are you adequately protected using this equipment? Well, we have already determined that total combustion of xylene is the worst-case scenario from a thermodynamic perspective. Now, to evaluate the impact of the energy release for total combustion, we must calculate the adiabatic temperature rise for this reaction. Here we use adiabatic to mean we assume all the energy released remains in the reactor. The adiabatic calculation provides an additional margin for safety because we ignore the beneficial effects of dissipating thermal energy to the surroundings. So we can see the adiabatic temperature rise in this system is 1,931 degrees Celsius. In reality, a steel reactor system would melt at this temperature. Since the system is not truly adiabatic, a significant amount of heat would be lost to the surroundings. Of greater concern is the pressure rise that would accompany this temperature increase. We can use a simple ideal gas law calculation to evaluate this pressure rise. Remember to use absolute temperature in this case. When we calculate the pressure increase, we can see it is only about 1,229 PSIG. That is well below the pressure rating of the vessel and the burst pressure of the relief device. So in this case, the potential for failure or release from complete combustion is not a credible scenario. So, are you adequately protected in this scenario? Yes, you are likely well protected. Would you have known for sure without doing the energy calculations? Probably not. And that's the point. Doing energy calculations is an essential step to helping ensure your safety. What you don't know about your project can hurt you. This is just one example of how to calculate and evaluate energy releases. There are many resources available where you can find thermochemical data to use. Resources include the NIST Chemistry Webbook, the CRC Handbook of Chemistry and Physics, and open literature.
More complicated energy calculations may require computer modeling using tools such as Aspen Plus. And of course, your supervisor and coworkers are excellent resources too. So if you're doing energy calculations for the first time or working with a new system, get input and help from others. Even if you're experienced, it never hurts to get a second opinion. Remember, doing energy calculations before you start will ensure all your energy goes into your safety and success.